This conference will now be recorded.
Great. So welcome everyone. So we have another session of OCP TAP, and today we have Kory Stone from. Sorry, where is this? So we have Kory Stone from Taitien Electronics. So Kory Stone is a technical marketing and has a strong engineering background. Has been over 25 years of experience in crystal oscillator industry, working for various manufacturers such as NDK, CTS, and SaRonix, if I'm not mistaken. Ronnie is based in Carlisle, Pennsylvania. In his spare time, Kory enjoys camping, kayaking, and playing disc golf with his wife, Linda. So
Please.
with no further ado, sorry?
Go ahead.
Yeah, so let's see. You want to say anything, Kory?
No, I just need this need to be made the presenter so I can share my screen.
Yes, yes, yes. Let me get that one sorted. As I was like going through this, today is like all complicated.
You're down under.
Yeah, I'm reversed, my orientation. I'm on this side of the globe. So let's see where is that, because again, I'm not on a normal setting right now. It's just like I'm trying to get all of that sorted. Let's see from my end. So let's see, where is that? And here, make presenter. Here we go. That should work for you now.
Okay.
Is it working?
My screen. Okay. Here we go. Okay. So hopefully you all can all see my
Yes.
screen. And I'm trying to get to the.
No, it should be the button underneath. Yeah,
Yep.
exactly.
Perfect.
And yeah,
Can you see that?
perfect. Let's go.
Good deal. So we lost a few minutes, so I'll go with a little bit faster pace.
No, no,
Can you?
it's fine. We can extend it in the back. That's fine because
Okay.
it's getting recorded anyways.
Great. So I'll give you a quick introduction to Taitien. I'll give you a brief overview of the products that we supply, and then we'll go into more detail on our products that are used for 1588 solutions or 1588 applications.
Wonderful.
So Taitien has been around since 1976. We went public in the year 2008, and so you will find us publicly traded on the Taiwan Stock Exchange. Our headquarters are in New Taipei, Taiwan. We're fully capitalized. We've got a strong quality system, and the reason for that is our chairman is Mr. S.T. Song, and he's the guy that founded the company and actually the guy that's still in charge. I think one of the things that makes Taitien the manufacturer that we are is the fact that we are able to, or that we do supply the full line of crystals and crystal oscillator products. And that really starts at the quartz bar. We actually grow our quartz, and then we process those bars of quartz into wafers and blanks. Those blanks then, those quartz wafers we use inside our products, starting with the pressure sensor or temperature sensor crystals that we produce, the surface mount and through hole crystals that we produce, and then we take those crystals and install them into our oscillators, the clocks, the VCXOs, as well as the TCXOs and the TCVCXOs, and then finally the OCXOs. And being able to offer the full line, being able to start at the bar quartz and wind up at the finished oscillator, again, is really a differentiator for Taitien, and one of the reasons why we are able to provide the breadth of product and the quality of product that we do. Our production facilities are located in Taiwan. That's where our headquarters are. We also have some production facilities in China as well as the United States. And so we're able to provide, really worldwide support for, our product offerings. Our quality, all our factories are certified to the ISO standards, and as well as we have several facilities that are qualified to the automotive standards, and then we're also getting ready for the quality systems, the HSPM standard that's coming out in China. So we are fully certified as a manufacturer and meet all the quality requirements that you would expect or need in your organization. One of the reasons why we're able to get that certification and maintain that certification is the in-house reliability testing capability that we have. We're able to do a complete battery of environmental and electrical and mechanical tests to the products, whether that's long-term stability or whether it's temperature characterization or Halt and Haas type of testing, as well as the environmental testing like shock, vibration, salt spray, gross leak, that sort of thing. And those would be all performed, really in-house to, the standard, whatever standards we're working to or working for you. Again, I think the reason why Taitien is the manufacturer we are is because we have all the technology we need in-house. We have over 25 patents for different types of oscillators, circuits, and manufacturing equipment. And quartz processing is uniquely different from what we see in a lot of other electrical manufacturing. And so the ability to fabricate the equipment that you need to cut the quartz and to manipulate the quartz is critical. I think we already had mentioned the testing background that we have. We have a strong test and algorithm type of technology. We have a great phase noise measurement capability down to minus 190 dBc. We are able to do all the tests that the 1588 standard requires, MTI, TDEV, holdover, those types of things. We've developed our own compensation algorithm, and we're able to do our own compensation of TCXOs, and that's over a very wide temperature range, minus 40 to plus 105 degrees. And we do all that assembly and test in-house, and we do that not only with the crystals that we make, but also with ASICs that we've produced in-house as well. So the ability to control the semiconductor, if you look at an oscillator, it's really only three things. It's a crystal, it's a package, and it's some ICs. And the fact that we're able to control those ICs, again, is a big differentiator for us. And I had mentioned, the fact that we do cut and manufacture our own quartz. The quartz is the key element that we use. It determines the stability and the reliability of the products we produce. If you don't start with a good quartz crystal, then you're not going to get a good quartz oscillator out there. And so really all of this comes together to provide a complete capability and enables us to provide products that we can certify to support your applications, not only today, but for 5 or 10 years down the road. So just to kind of summarize that, we've been in business for 40 years. We've got a great database of design and manufacturing. We've got complete vertical integration, from growing the quartz to the final end product. We've got complete in-house capability, and all that leads to an excellent capability from a product standpoint. And we'll start talking about those products. And the most basic element that we have, the most basic product that we produce is the crystal. It's really that quartz wafer, packaged inside a metal or a ceramic package. What we're looking at here would be our most popular types of crystals. These are our surface mount crystals, and generally they range in size from 5 by 3.2 to 1.6 by 1.2 millimeters in terms of size. The size of the crystal is important. The higher in frequency it is, the smaller the crystal gets. And so what we'll see is that, you know, the smaller packages have a little bit different frequency range, particularly on the bottom side of the frequency. The smaller the package, the higher the lower frequency is. And so, you know, it really takes something to package that 2 pounds worth of stuff in that 1 pound package. And in that regard, you know, whenever you're selecting the crystal for your particular application, you know, pick the biggest crystal that you can put in your application. 3.2 by 2.5 millimeter is probably the most common crystal today, and that's because it operates over that 12 to 60 megahertz frequency range, and that's a, you know, basically where a lot of us live, breathe, and work in terms of the crystals that we need to operate, the 25 megahertz crystals that we need for our processors or so on, the communication protocol that we're working for. So, but as we go down in size, like I said, the low end of the frequency range goes away. The resistance of the crystal starts to go up on us, making it a little bit more power hungry and a little bit more difficult to use. And so that's why we recommend, you know, using in a sense, the biggest package you can in your particular application. But if you need a small size, we have the small size, so we're able to support, you know, whatever your application demands in terms of package size or crystal performance. The only thing you can do with a crystal is put it in an oscillator. And so if we look at a crystal, it's really just that quartz wafer inside a package. And now whenever we talk about clock oscillators, we talk about putting that quartz wafer in a package with a semiconductor. So X is the typical thing that we use, or the typical letter that we use to represent a crystal. XO is the typical nomenclature we use to represent a crystal oscillator, X for crystal, O for oscillators. And this is our CMOS type of oscillators. Again, they come in very similar package sizes to the crystals, 7 by 5 all the way down to 1.6 by 1.2 millimeter. These would be the most popular package sizes that we have out there today. And again, I think the 3.2 by 2.5 millimeter package is the most common. Because these are CMOS oscillators, they're limited in terms of their frequency to about 200 megahertz, but they are able to operate over a 1.8 to 3.3 volt supply voltage range. And, you know, the jitter performance is relatively good at less than a picosecond and a half. We do offer differential output oscillators, the PECL or the LVDS and the CML or the HCSL types of oscillators. These oscillators allow us to go up higher in frequency due to the use of PLL technology, and they also provide us with good noise performance, less than 350 picoseconds or 350 femtoseconds. We actually just introduced an oscillator series with a low jitter, less than 100 femtoseconds worth of jitter. And similar to the CMOS, they come in the 7 by 5 packages and smaller, although the differential die and the differential ICs tend to be a little bit larger in size than the CMOS ICs that we work with. And so the package sizes tend to be a little bit larger as well. The larger package size gives us the ability to put a little bit better crystal in there, and that's one of the reasons why we're able to obtain a little bit better jitter performance, not only because of the differential output, but also because of the better quality crystal that we're able to use inside the larger package. Again, these work on supply voltage ranges ranging from 1.8 to 3.3 and 3 volts, and 5 by 3.2 is probably the most popular package size for differential oscillators, although 3.2 by 2.5 millimeters is growing in popularity. The 7 by 5 packages are constrained, supply constrained in the marketplace. The manufacturers are eliminating 7 by 5 millimeter package capacity in favor of the smaller packages, the 5 by 3.2 or the 3.2 by 2.5 or even smaller. And this is really driven by the automotive marketplace. So if you're using an oscillator, it's in a 7 by 5 millimeter package, I would encourage you to go out and verify your supply chain, verify the lead time, and verify the availability of these guys, because these packages are getting a little bit more difficult to get. So just kind of a word to the wise, so to speak. And for your new designs, look at the 5 by 3.2 or the 3.2 by 2.5 millimeter packages. So we have X for crystals, we have XO for oscillators. The next thing we have is VCXO, and VC stands for voltage controlled crystal oscillator, and or VCXO stands for voltage controlled crystal oscillator. And here, we generally talk about the stability of the oscillator. How accurate can we make the oscillator to the particular frequency that we're looking for? VCXOs go the other way on us. We actually have a tuning port available on the oscillator, and you're able to control the frequency of the oscillator by an analog voltage that you put on that control port. And this would be to phase lock the oscillator to an incoming signal that you might have, or to modulate the oscillator for a particular protocol that you might be using. But it does give you the ability to, vary that frequency up and down. Similar to what we saw in the Peckel oscillators, they actually go up to 2.1 gigahertz in terms of their frequency range. We're able to produce the differential output oscillators as well as the CMOS or single-ended output oscillators, and really these are available for use almost anywhere in your circuit applications. Again, the VC, or the voltage control crystal oscillator, gives us the ability to change that frequency to match the particular application that you have. So we talked about VC, or voltage controlled. The next type of oscillator that we have are TCXOs, or VC TCXOs, and in this case the T and the C stands for temperature compensated oscillator. Whenever we look at a crystal or a crystal oscillator, there's the primary source of error that we see in the oscillator is temperature. And there's a couple of ways we can do that or fix this. One is we can control the temperature of the oscillator, or we can compensate the oscillator for any changes in temperature that it sees. And that's what we do in the TCXO. And that's why we refer to it as temperature compensated crystal oscillators. We basically take a VCXO, we hook it up to a temperature sensing network, and we adjust the frequency of the crystal for changes in temperature that we see outside. So we're sensing the temperature and then adjusting that crystal frequency to offset any changes that it might want to make as a function of temperature. The TCXOs come in very similar packages to the clocks that we saw. They come in the 7x5, the 3.2 by 2.5, the 5 by 3.2. But then they also come in a little bit larger package, in this case, a 14 by 9 millimeter, so we can get to higher levels of performance, better noise performance, or better temperature stability. And whenever we talk about temperature stability for clock oscillators, they tend to go anywhere from 100 parts per million to 10 parts per million. Temperature compensated oscillators tend to go from 1 or 2 parts per million down to 0.1 or 0.2 part per million. This would be our standard type of VC TCXO or TCXO, and so they would tend to be more the 1 to 2 part per million type of stability. And we do have higher precision TCXOs that we offer. These again are in the 7x5 millimeter types of packages. They offer the logic outputs that we saw before, but again, these have the tighter stabilities, 0.1 part per million or 0.2 part per million over a very wide temperature range. And so now we're starting to get very accurate, 100 times or 1,000 times more accurate than the typical clock oscillator might be. And these would be, now we're starting to approach products that you might want to use in your, your 1588 application, depending upon, whether it's a slave or a master, or, where you have it, how you have your network configured. These guys tend to be in the 7x5 or the 5 by 3.2 millimeter package. And, I would recommend, again, the 5 by 3.2 millimeter package wherever you can. And this is because of price and availability reasons. So, we have the high precision TCXOs, or whenever we have a TCXO that we're able to adjust the frequency, to adjust it for aging or to calibrate it, or whatever the reason may be. That's why we add the the VC in front, or the voltage controlled temperature compensated crystal oscillator. And so that's a little bit of the jargon that we use in our industry. The next step up from TCXOs is OCXOs. And as I mentioned earlier, we can either compensate the oscillator for changes in temperature and changes in frequency that occur as a result of temperatures, or we can control the temperature of the crystal. And that's what an OCXO does. So different than a TCXO is temperature compensated crystal oscillator. This is OCXO, or oven controlled crystal oscillator, and it does exactly what it says. We take the crystal and we put that crystal inside an oven, and we control the temperature of that oven to a very precise degree. So if it doesn't see any temperature changes, it doesn't have any error being introduced. And whenever we talk about temperature control, we talk about temperature control down to milladegrees. And this is generally, if your outside ambient is 70 degrees centigrade, we have to heat the crystal up inside probably to 80 or 85 degrees centigrade. We cannot cool the crystal down. We can only apply heat to the crystal. That's why it has to run hotter than your outside ambient, because if we ran it at 60 degrees, the temperature of the oven was 60 degrees, and your outside ambient went to 70 degrees, then we would lose control of the crystal. So the crystal is always hotter, or the oven is always hotter than your highest ambient. And this is one of the reasons why, you may only be able to find an OCXO up to 85 degrees, where you can find a TCXO to a much higher temperature. And that's because, at 85 degrees centigrade, we're heating the crystal up to about 100 degrees centigrade or 95 degrees centigrade, and that starts to hit the limit of the semiconductors that we're using, the junction temperatures and things for the semiconductor that we use inside. So sometimes we are temperature limited. But by the same token, where we control the temperature to milladegrees, the output frequency, the oscillator is actually controlled to parts per billion. So in clock oscillators, we were talking about clock oscillators being 100 part per million in terms of stability. We were talking about the temperature compensated oscillators being about 1 part per million in terms of stability. And we talk about OCXOs in terms of 10 or 1 part per billion. So again, 1,000 times greater or more stable than the typical TCXO might be. And these would be the ones that you would tend to use as your master clocks, or your reference clocks in your telecom systems. And these would comply with the various ETSI standards or other standards out there for SDH or SONET types of network applications. Here we're looking at our through-hole packages, and because of the oven, the OCXOs tend to be much bigger. This is 1 inch, 1.5 inch by 1 inch in rectangle, and that's because, again, we take a crystal and we stick it inside that oven, and then we put that inside the package, and that really drives our size. And we also like to insulate the crystal. We like to insulate that oven so it can't see changes in the outside world. One other change we make is we actually use a little bit better crystal inside the OCXO than we do in the other oscillators. As I had mentioned, the bigger the crystal we can get, the better the performance we can get out of it. Because we're looking for part per billion stability, we can no longer use the small quartz wafers that we like to use. We use a larger crystal, perhaps an SC cut crystal versus the AT cut crystal, SC standing for stress compensation. And so it gives us a more relaxed body to operate over the temperature range, or operate over the life. But we do have smaller sizes than that. We have, the 20 by 20 millimeter size, a little bit smaller than an inch square. And we also have the 14 by 20 millimeter packages that are basically the 14 pin dip type of configuration. The other thing about OCXOs is they do run on a little bit higher voltage, 5 volts in this case, or even higher, depending on the application. And that's because, again, we've got to get some power inside that package to heat up that oven. And so 1.8 volts just doesn't do that for us. The other thing is the frequency range is a little bit more limited. In this case, on this screen, what we're looking at is 5 to 40 megahertz, and that again is because of the type of crystal that we use inside and the frequency ranges for those types of crystals. Not every crystal is able to achieve a 1 part per billion or a 10 part per billion or a 50 part per billion type of stability. It takes a very high quality crystal and again, a little bit lower frequency because it's a little bit bigger and gives us a sturdier platform to work from. But we do have surface mount versions of these, and these tend to get a little bit smaller. Here we have a 25 by 22 millimeter package, and to me this is kind of the standard package for OCXOs or high stability OCXOs in a surface mount configuration. We can do almost everything that we do in a through-hole package in this particular package size, but again, we understand that you've got 2 pounds worth of stuff that you want to pack in your 1 pound package, and so we do offer smaller sizes, 14 by 9 millimeter, like we saw on the TCXOs, and we're actually coming out with smaller packages. I think we're in the process of getting ready to release a 7 by 5 millimeter OCXO. These tend to lose stability because of the small size. The oven doesn't have as much insulation around it, so it's more sensitive to temperature, and so we do see temperature variation in these smaller packages, but they are good for us in terms of, you know, being able to fit in those small footprints that we're looking for. So the performance of the smaller packages tends to go away on us versus the larger packages. And again, from an OCXO standpoint, you know, if you're looking at cost versus performance, you know, if you're looking to get the same performance out of a 14 by 9 package as you are out of the 25 by 22, this 14 by 9 is going to be more expensive. So if you can use a little bit bigger footprint, that helps get you a little bit more economical product. It helps get you a little bit better performing product, and should actually be a little bit more available. So I think everything gets better whenever you can use a slightly larger package, or whenever you use the biggest package that you have available or that you can tolerate in your application. And then comes the big boys. These are our double ovens, and this is where, you know, if we take a crystal, put it in an oven, we can control the temperature of that oven to a few milledegrees. But if we take that crystal in an oven and stick it into another oven, then we can actually get better temperature control down to almost microdegrees. And this gives us a little bit better stability over temperature, a little bit better stability in terms of life, you know, than we see with the single ovens. Another thing that we do in the larger package sizes, and these are some of our ultra low phase noise, these would be our 25 by 25, or again, that 25 by 22 millimeter type of package, is we're able to add some filtering to the output. The ability to add some filtering gives us that improvement in phase noise that we're looking for. Without the filtering, we're looking at maybe a minus 160, minus 165 dBc noise floor. With filtering, we're able to get minus 180, minus 185 dBc in terms of performance. And this also reflects back into you know, the other noise measurements that we make down the road. Again, one of the things we do to reduce phase noise is increase the signal output. And so you'll see these the low noise products tend to use 12 volts rather than, you know, the lower voltages. And again, this gives us just an ability to drive the crystal harder. We get a better signal to noise ratio, and so we get better noise performance out of the oscillator. And I apologize, here we go. Losing part of my screen because of the go to meeting thing. So anyways, you know, beyond the OCXOs is our timing modules, and you know, here what we're looking at, you know, and up until this point in time, we've been talking about oscillators, and the performance of the oscillator is dictated by the crystal that we put inside the oscillator. With our timing modules, we actually discipline the oscillator, or discipline the crystal with an external signal. And then because of the stability of the external signal, we're able to train the crystal to perform in a similar manner. And the disciplining can either occur either because of the GPS signal that you might get from your GNSS constellation, or it could be the 1 PPS that you get out of your GPS chip or something like that. So we can use straight GPS to discipline the oscillator. We can use a 1 PPS signal to discipline the oscillator. And then again, the oscillator, the longer we discipline it, the better it gets trained and the better the long-term stability is. So if your GNSS signal goes away, or if your 1 PPS signal goes away, the oscillator is able to maintain its stability for a longer period of time because of the training or the discipline that we did with that external signal. And that's referred to holdover, the ability of the oscillator to maintain its frequency once it loses that incoming source. And, you know, we're able to achieve 1.5 microseconds worth of holdover with some of our larger ones. And actually, we've introduced an atomic standard that's able to achieve, you know, 1 microsecond worth of holdover in the 72-hour period. So we're actually stepping up performance as we move into these timing modules, and these indeed are the types of things that we would want to see in master clock types of applications. So now that was a rundown on our product line, from the low-end quartz crystals all the way up to the high-end discipline timing modules. And hopefully that wasn't too fast for you guys and you're able to keep up with the differences as we went through the product areas. But now we'll look at some of the oscillators specifically that are say used in 1588 applications, and we'll look at some of the performance levels, the MTI, the TDEV, and those types of things, the performance levels that you're interested in those types of applications. And so we'll take a look at the TCXOs. We have a couple of those tight stability TCXOs, our TT type and our TW type, which are able to achieve that sub ppm stability. And they're able to meet the different GR 1244, GR 253 types of standards, as well as the different ITU standards. And then we'll look at a couple of our OCXO types, some of the more common types that will, again, you know, meet those mask requirements for MTI and TDEV and the different standards that we have set. Just a little housekeeping for this, you know, because the equipment that you use can be important. The bandwidth that you have in your filtering is certainly important. And so, you know, all the testing that we see and all the testing that we'll look at down the road or in the slides coming up, we're done with 500 kilohertz to 4 megahertz bandwidth for the OCXOs, and generally a 2 megahertz to 8 megahertz bandwidth for the TCXOs, and maybe a little bit lower frequency. And this is the high stability TCXO that I was referring to, 10 to 52 megahertz from a frequency range standpoint. It's able to hit 50 part per billion stability over a -10 to 0 to 70 degree C temperature range. And so rivaling OCXOs in terms of its temperature stability, which is very good for a TCXO. Lower supply voltages, 2.5 and 3.3 volts, able to do CMOS or clip sine wave out, and pretty reasonable phase noise performance, -145, roughly -145 dBc at the 1 kilohertz bandwidth. And this is a little bit small to see, so we've made it a little bit bigger on this slide so we can actually see that it's about -140 at a kilohertz, -153 or 154 at 10 kilohertz, and then it's got a floor of about -157 on out. And so this is the type of thing that you'll find in these small size TCXOs. This is 5 by 3.2 millimeters in terms of size, so very, very small, very, very low power consumption, but still relatively decent phase noise performance and jitter performance. The next thing that we worry about in terms of oscillators, and I hadn't really referenced it up until now, is the long-term stability of the oscillator. I don't go as fast as I used to when I was young, and crystals change their speed as they get older as well. And so this is what we're looking at here, is this aging curve of the oscillator. You'll see that it speeds. This is a logarithmic scale, by the way, so you can see that it's relatively fast, you know, in its young days, and then the aging slows down as we go over a period of time. Over a 20-year period of time, we get a minus 1.63 part per million frequency shift. And this is one of the reasons why we have a voltage control port on the TCXO. So if this oscillator ages a little bit, we're able to adjust it back to the center frequency, and we're able to keep it right on in terms of the performance that we're looking for over a long period of time. We actually have oscillators that have been running for 20 years and, you know, or so in terms of time period. And so we're actually able to, you know, this is not only extrapolated data, but it's actual measured data as well. You know, we talked about temperature influencing the frequency. We talked about time influencing the frequency, and also vibration can influence the frequency of the, you know, of the crystal. In this case, a TCXO. And so we have a low G sensitivity TCXO, and here as we, you know we've got some fans in our system. We know that it there's other things that can induce mechanical vibration or mechanical noise into the oscillator. And so we've introduced a low G sensitivity oscillator, and basically what it does is it eliminates any frequency variation as a function of that dynamic environment or that vibration. And you can see that it's typically about about 0.1 part per billion per G in terms of the sensitivity. But you know, depending on what we're looking for, this can be a significant influence. Typical TCXOs are probably going to be in the 0.3 to 0.4 part per million per G area to give you a look at the difference in performance. And, you know, so if you have the TCXO sitting right by a fan, and you've got that fan introducing some microphonics onto the PC board, you could be wondering why you don't see the same frequency stability out of your oscillator, and it's probably because of those vibrations. And you might want to either move the oscillator or get a low noise, a low G sensitivity oscillator such as this. These tend to be a little bit higher drive capability. Again, that higher drive gives us a wider signal to noise ratio, and that gives us a little bit better noise out of the oscillator. Typical stability on this type of part right now is about a half a part per million over the minus 40 to plus 85 degrees C temperature range. But, you know, it's an option for you if you need to get heat out of your box and you need to use fans, then this would be an option for you. A little bit bigger, 7 by 5 millimeter in terms of size, and that's because of the extra platform that we need to put inside to help minimize the crystal and the effective vibration onto the crystal. This gives us a look at the phase noise, and very similar phase noise performance to what we saw earlier. Minus 147 at the 1 kilohertz offset, minus 157 or 155, excuse me, at the 10 kilohertz offset, and then a floor of about minus 157, 158 dBc. So relatively good noise for a small size oscillator in this footprint. Typical type of aging data, in this case, we're actually a little bit better, minus 1.36 part per million over a 20-year period of time, and minus 0.27 part per million for an actual year in operation, or an actual 5 years at 0.61 part per million. A lot of manufacturers, because aging takes time to measure, you know, you got to measure the frequency of the oscillator every day. You got to make sure that the temperature is the same when you're measuring it, so you're not seeing any influences from temperature. And so aging is a difficult parameter for manufacturers to measure. Oftentimes what a manufacturer will do is they'll measure it over 10 days and then extrapolate out to longer time periods. You just need to make sure that your manufacturer is doing the appropriate aging, and then making sure that they're using the appropriate curve fit process, so that they don't show you, you know, something that's unachievable for the oscillators. This is still an area, aging is still an area where manufacturers might play some specsmanship, so to speak, in terms of of how long they measure it, how they extrapolate it, and what temperature they measure it at. Our aging data is done at 40 degrees centigrade, and we know that as the temperature goes up, the aging will accelerate. A lot of manufacturers might specify the aging to occur at 25 degrees or something like that. Well, 25 degrees is not practical because you're not putting the oscillator in a 25 degree C environment. Even if you put your system is sitting at 25 degrees centigrade, the temperature rise inside your box is probably 10 or 15 degrees. And so you need to make sure that your manufacturer not only is doing the proper curve fit, but actually doing it in the appropriate environment, not measuring it at 25, which we'll see good results, but measuring at 40, which is a little bit more stress on the oscillator, will give you a better reflection of how the oscillator will perform in your application. Now we'll get a look at some M-type performance, and I'm assuming that everybody's familiar with these types of things, so I won't go into a definition, but we are comparing this to the ETSI PDH standard. That's the mask that we have above that, and the blue line is the performance of the TCXO. This is with a 4 megahertz filter, as I had mentioned before, and so, you know, in that regard, we're filtering out, you know, the higher frequency noise that might interfere with us. And you can see over 10,000, excuse me, 100,000 second interval, we're actually able to meet that mask set as required. So this would be an you know, a type of a clock that you could use as a boundary clock or a slave clock or something like that in your applications. This gives us a look at TDEV, and you know, TDEV and MTI, you know, are a good look at almost the same thing. The MTI gives us a look at the range or the of time error that we would see from the oscillator, and the TDEV would tend to give us a look at the accumulation of time error in the application. And again, we're able to meet the ETSI map or the ETSI mask with our TCXO, and this is a time scale. This is time in seconds across the bottom, and then the observation window or tau across the bottom. Now we'll step it up a notch. From a TCXO, we'll look at an OCXO, and again, TCXO stands for temperature compensated, and so there's really only so much we can do with that. OCXO stands for oven controlled, and in this case we're able to achieve a stability of 10 parts per billion over a minus 40 to plus 85 degree C range. So very, very stable oscillator, good for long periods of time, able to work on smaller supply voltages, 3.3 or 5 volts. But you'll see here, one of the things that we do get over a TCXO is the increase in power consumption. The oven draws current, and so we look at, you know, a half a watt power consumption at 25 degrees. And as we go colder, this power consumption will go up because it's got to put more heat into the part. As we go hot, the power consumption goes down because, you know, we're getting more heat from the outside environment. As I had mentioned, the long-term stability of the OCXOs, not only in terms of temperature stability are we better, but also in terms of aging stability. And we look at plus and minus 1 part per billion per day, or 200 part per billion over a year, and less than 1 part per million over 10 years. And you can see from the TCXO data that we looked at earlier, this is about 2x better than what we typically see in a TCXO, or and so this is certainly suitable for your PTP type of applications. Over here, we can see a temperature stability test for the oscillator. This is minus 40 degrees, and this is plus 85 degrees. And you can see that over temperature, it is actually holding better than 3 ppb in terms of stability. And so very, very accurate, and able to provide an accurate time base to your system as you move forward. We can look again at the phase noise of the oscillator. The OCXOs tend to have a slightly better phase noise performance. Here we look at minus 157 at a kilohertz offset, minus 160 at the 10 kilohertz offset, and about a noise floor somewhere around minus 165 dBc. And this is data that your manufacturer should be able to show you, even this aging data. They should be able to supply that to you and show you a reasonable amount of aging data and a reasonable performance over time. And this would actually be, looks like about 9 months worth of data. And you can see that the stability is less than a couple ppb over that time period. So we try and be pretty conservative in our specifications. We're manufacturing a lot of units to meet these specifications, and so we really look at we apply a Six Sigma mentality to the way we put our maximum values. We test a bunch of them, we verify the statistical performance of it, we multiply the error by the Six Sigma value, and that's how we set our maximum level, so that we're certain that whatever we ship to you is meeting the specification that we provide to you. Time interval error is, or TIE, is the source of the TDEV and the source of the MTI measurements that we take. And here we can actually see some raw TIE data. This was done on with an ADI 9548. You can see that the TDEV of the OCXO typically is less than a half a nanosecond over any long interval period. And so in that regard, that gives us a great MTI performance and a great TDEV performance. And this is multiple samples that we're looking at. And you can see that we're well below the mass. The red lines would be the different mass sets that we're checking the part to, and you can see the actual performance lines, down below. And there's you can see that we're actually looking at part and 10 to the 10th in terms of the maximum TDEV of this particular part, well below the mask sets of the different standards that we're trying to get to. This is a little bit better OCXO. The OCXO that we were looking at before was a 14 by 9 millimeter, and it was kind of an open package. This is a 20 by 12 millimeter OCXO, and it's in a hermetically sealed package. So it gives us a little bit better performance overall than what we typically see. Power consumption is the same as what we saw, before. This is a temperature stability is listed as 100 ppb, but this is overall. So this includes the calibration, it includes temperature, and it includes some aging period. And the aging rate is similar to what we saw on the other OCXO, and the performance of the OCXO will be better, will be about the same from a phase noise standpoint. What we'll see differently is the TIE performance here. The TIE performance is relatively small at about 20 nanoseconds. And so again, we can take, but that's with a relatively narrow bandwidth filter, a wideband filter. The narrower bandwidth, the better this performance becomes. And this is over a 24-hour period of time. And actually, in this case, it gets to be a little bit higher. This is we actually start bumping into the mask line for the ETSI standard at a part in 10 to the -8. So we're not pulling cherries out. We are showing you actual measured data. In this case, we're bumping right up into that mask set. Here we get a little bit, this is the MTI performance, and the MTI is a little bit softer measurement. It takes out some of those peaks for us, and so we're a little bit better performance from an MTI standpoint relative to the mass sets that we're trying to achieve. And then this would be a 40 megahertz version of the same part. A little bit more grace for us in terms of the difference between the performance of the oscillator and the maximum performance that we're allowed. Now we get into some of our higher end, more more insulated type of OCXO. This is one of our real low phase noise OCXOs, and so you can see we've got a noise floor down close to minus 170 dBc. So in that regard, really good for, I'll say, microwave types of applications or test and measurement types of applications, or even your telecom types of systems. 12-volt supply, again, trying to put some power into that to help us with our phase noise performance. Relatively low stability, 100 ppb over minus 40 to plus 85, but where we see the difference is in the performance of the oscillator. Here we can see the TDEV performance of the NA type at 12.8 megahertz, again with a 1 megahertz loop filter bandwidth, and the TDEV performance again is about twice as good as what we need it to be relative to the PRC type of the ETSI PRC mask set. And this would be the M-type performance, similar type of margin in terms of the PRC performance, part in 10 to the minus 8 over a long observation period, a part in 10 to the minus 5 parts in 10 to the minus 9 over a shorter observation period, but relatively linear, indicating that it's more the flicker noise in the oscillator rather than white noise or anything like that. Getting close to the end here, I think, and this would be another one of our low noise oscillators. In this particular case, we can actually do the frequency up at 100 megahertz. So we can do 10 megahertz and 100 megahertz, and the 100 megahertz gets us a little bit closer to, perhaps the ultimate frequency that we're looking at. Phase noise performance is very similar to what we saw in the last unit. This one's surface mount. I believe the previous unit was through hole, and so we've got it in multiple configurations. The larger packages just allow us to do more filtering inside. The lower noise again results in better MTI or TDEV performance. In this case, we're looking at MTI, and we can see that, again, under short observation periods, we're looking at about 5 parts in 10 to the minus 10th, and over longer observation periods, 5 parts in 10 to the minus 8th. But of course, the mass set is somewhere around 8 or 9, 10 to the minus 8th. So in that regard, we're under the mass set for the GR1253 or the GR1244. I think we're going to have to work on our coloring on our slides so we can see the difference between those two mask sets. This is the TDEV performance, and again, multiple samples over a relatively long observation period, 10,000 seconds, and well under the TDEV requirements for the GR1244 and the GR1253. And then frequency can be an issue for Taitien because we make our own crystals. It's not so much of an issue for us, although you can see that it is a little bit higher from a TDEV standpoint for the 30.72. In this case, we're looking at the GR1244 mask for TDEV, and we're up at about looks like 2 or 3 times 10 to the minus 9, in terms of TDEV performance. Relatively linear in terms of its response, though, indicating good characteristics from the OCXO. And this is some of those discipline timing modules that I had mentioned before. This is one of our, this is a GPS discipline timing module, and so it takes excuse me, I'll take that back. It's a 1 PPS discipline timing module, so it takes 1 PPS signal in from your GPS or whatever satellite system or whatever reference you're piping into it, and it's able to discipline the oscillator better than 10 and to the minus 12th. So we're basically achieving atomic-based stability with a quartz-based type of product. And so the advantage is the cost. This is about 10 times lower cost than the typical atomic standard would be. And so in that regard, we're able to provide almost atomic type of stability with a quartz-based oscillator almost at a quartz-based price. And the 1 PPS accuracy is better than a nanosecond RMS in terms of phase discipline. So in that regard, very tight stability there as well. And the holdover is the kind of the magic for these particular parts. What happens if we lose lock, or what happens when that satellite signal goes away? And the holdover stability of this part is better than a microsecond and a half for 3 days at a relatively constant temperature, and about 100 microseconds for 7 days, again with a relatively constant temperature. Has an oven inside. It is a quartz-based OCXO that we're disciplining with an incoming 1 PPS signal. So we've got an OCXO inside of there, and then we also have some memory that we put inside of there so that the oscillator performance, the OCXO performance, can be compared to the 1 PPS performance, and then we can use that 1 PPS performance to discipline or to steer our OCXO for temperature variation and for time variation, and get a very precise signal over time. And that's what we're looking at in this particular case. We're looking at holdover performance, and the blue line is how the temperature is performing, the red line is how the frequency is performing, and you can see over a 25-hour period, it's better than 200 nanoseconds over that period with a 20°C change in temperature. So good performance in that regard. And I'm just going to look here a minute because I don't have. There we go. So we can look at the holdover performance of the OCXO. Let me just move this a minute. There we go. And so again, this is indicating the blue line's the temperature. So we've got a relatively constant temperature, and over 24 hours we lose about 436 nanoseconds. So in that regard, the holdover performance of the OCXO is relatively good. If we would compare this to another OCXO, that would be probably down in this area about -1,000 or -1,500. Maybe we probably need to put that performance on here so we can see that. And this is our atomic clock. This is the final one that we'll be looking at. This is a DTA 101. It's 50 millimeters. 50 millimeters. It does have CSAC type of footprint, so it is a chip scale atomic clock. In this case, it's got the low power operation, -170 milliwatts. If you don't need low power operation, then don't ask for it, because the 170 milliwatts does drive the cost of the product. In this case, we have a 10 megahertz output. It takes a 1 PPS input and provides a 1 PPS output, disciplined to better than a nanosecond RMS in phase, and again, better than 10 to the -12th in terms of frequency. And it does have a built-in phase meter, so we can, measure that. We can control it with an RS-232 input, and as I mentioned, it is compatible with the CSAC products that are out there, but the one thing that we will find is that the phase noise is a little bit better than the typical CSAC that you see out there, and so in that regard, that gives us a better look at the clock over network type of application. This gives us a look at the holdover of the phase data of the DTA 101. In this case, it's over 72 hours, and the holdover performance is better than 400 nanoseconds over that time period. And so in that regard, that more than exceeds the holdover requirements that we're looking at. You can see over a day, it's as we go longer than a day, the holdover performance really doesn't change that much. And this is because of the rubidium standard that we use inside. Very fast warm up, which is another thing we didn't really cover in the OCXOs. OCXOs, because we do need to heat the crystal up to a very high temperature, take some time to warm up. Typically, that warm-up period can be as long as an hour for the frequency to settle into something, a part in 10 to the ninth or a part per billion to the relative frequency that it's going to settle at over a day. Atomic standards don't really have that problem. They're almost instant on. You can see in less than 2 minutes they're at the frequency that they're to be, and they carry that frequency out for a long period of time. So that's really what we had to share with you. That's our product offering, from quartz crystals to atomic standards, a little bit about the performance that you'll get out of each type of oscillator. And hopefully we've given you some information that will enable you to make a better selection in your crystal oscillator for your next application. So
wonderful. Thank you very much, Kory. So let's go for some questions, if you don't mind.
Okay. Mm-hmm.
So we'll start with Stavros has some questions. Stavros, do you want to unmute and ask questions? Let's see, Stavros.
Yeah, hi. Well, thanks, Ahmad. No, I was wondering if your DTA atomic oscillator is commercialized. And then I had another question, what type of atomic standard do you use? But you answered it just at the last second of your presentation.
Okay.
Which is a rubidium based
So
on.
whenever you say commercialized, the answer is, I think, yes. It's available for delivery. We do offer it, for sale at this point. So we are actually shipping this product right now. Demand has been quite strong. So I'm not sure what we'll see from a lead time standpoint. Miguel's probably closer to that than I am. But like I said, demand has been pretty strong, and that's tended to push our lead times out a little bit.
Okay.
Yeah, the lead time for this product, fortunately, is pretty long. It's a little bit over a year, about a year currently.
Oh.
Yeah.
All right.
Is that for both models, Miguel? Is that for the low power as well as the higher power?
I believe that that's for the low power, but I think the higher power is pretty similar. That's one of the reasons, at least at the moment, we're pushing the quartz solution, the DT5151, especially in the situation where you don't need the low power, because the performance is really there. It's a great product, I think, from all standpoints. And if you're plugged in and power is not an issue, this is a great product. Plus, it saves you a bunch of money.
Okay. And
Yeah.
on this one, I had another question. Unless you have something else to say, Kory.
No, I think the points that Miguel made were correct. If you're always going to have a 1 PPS input available for the oscillator, then this will perform as well as an atomic standard.
And does this really? I imagine this is has something like a learning mechanism, like a compensation internally. Does it
Yes.
require to be locked onto a GPS for a certain period, or external reference PPS for a certain period of time?
Yes, so you're absolutely right. There is an algorithm that we use inside that provides the correction and update to the oscillator. The longer it's locked, the better that algorithm becomes. And at this point, we would look for that lock to be over 24 hours.
At least 24 hours. For this, the performance that you present here.
Correct.
Maybe I can ask around that one. Is like there is a tau associated with that algorithm? Is that tau variable? Can you adjust it, or it's just like a closed box? You just provide the PPS and fingers crossed things will work. Like which kind of is that?
Well, you don't have to cross your fingers, and I believe that is a fixed tau.
Oh, it's a 6 tau. Okay.
Okay.
And is it disclosed? What is it? Is it like 10,000 second, or like, because that is driven from your Allen variance, right?
So I would default to our engineering team. I don't have that number.
I see.
So, but we can get that for you and get back to you with that.
Yeah. Stavros, sorry, I think I interrupted you. Go ahead.
No, it's okay. Thank you.
So one more question, Kory. Like when you choose between low power and high power, what is really changing in the rubidium cell? Like, is there is it like an oven controlled rubidium, or like what is going on? Like, I just want to know a little bit more.
Yeah, and that is that's more related to the control circuitry and the ICs that we use inside.
I see.
So that's really where most of the power consumption is.
I see. So let me ask you another question that is, I think, was right in the beginning of your presentation, that you mentioned a bigger package for a given application is suggested. I mean, why is that so? Where is it coming from? It's pretty interesting to me, you know.
So it really comes down to the mass or the type of crystal that we're able to use, the mass of the crystal. A larger mass for the crystal gives us a more stable environment. It's affected less by the manufacturing stresses or the mounting stresses or the different types of conditions that we would expose the crystal to. The crystal is actually in there moving at millions of times per minute or per second, excuse me. If those oscillations make their way out to the edge of the crystal and reflect back in, that gives us interference modes, and that affects the stability of the crystal. And so the larger quartz wafers are less affected by those types of interference modes. It's also a larger mass. If you take the fundamental frequency of this is for an AT cut crystal. If you take the fundamental frequency of the AT cut crystal divided into 66, that gives you the thickness of the crystal in thousandths of an inch. And so basically, as we go up in frequency, the crystal starts to get very thin, and that lack of thickness or that thinness of the crystal, again, increases the stresses and that it's affected by the mounting stresses and that sort of thing. So the greater the mass of the crystal, the more stable environment we have for that oscillation inside. And so we're able to achieve a higher stability. An SC cut crystal is about 1.5 times the thickness of a AT cut crystal, and that's one of the reasons why whenever we look at a real stable platform, we'll go with an SC cut crystal, because it gives us a bigger quartz wafer and a more stable stress compensated platform to mount our crystal with. So
So another question is about the tuning fork, and usually like the VCXO, I mean, in general, or TCXO, I mean, VCX, whatever you can change. Usually, how far you can push that, like in terms of it's a percentage. Let's say for 10 megahertz, how far you can push up or down the frequency.
yeah, so the crystals we're talking about here are the AT cut crystals, which are a thickness shear. If you would look at the side of the crystal, it would be like two plates rubbing back and forth together like that, which is different than the tuning fork crystal that you had mentioned earlier. Tuning fork crystal is actually the shape of a tuning fork, and the oscillation occurs because the piezoelectric effect bends one of the tines back, and we set up an oscillation between the two tines. The tuning fork is relatively low frequency, good to from 10 kilohertz to 100 kilohertz. We use the AT cut crystal because it gives us the widest frequency of range of operation. We can get an AT cut crystal to vibrate anywhere from 500 kilohertz to several hundred megahertz, depending on the overtone and that sort of thing. So and I guess I might have lost track of the question there, but the AT cut crystal.
The range, they asked, yeah.
Pardon?
I asked the range. The range can change. Like,
Okay,
because you were
so
lost
the
the track.
tuning range, if we have the tuning range is generally going to be I'll say a couple of hundred parts per million. plus or minus a couple hundred parts per million. We like to keep that as small as possible because it's an instability in the crystal, and the wider that pull range is, the more difficult it is to pull it over that range. We can get it plus and minus 1,000 parts per million using some, hyper abrupt bractors and those sorts of things, some wide pull devices. But typically in a VCXO, it's going to be a couple of hundred part per million. In a TC VCXO, it's going to be plus or minus 10 part per million. Really enough to cover, with a VCXO, you're going to want to modulate it so the pull range is farther. With a TCXO, we really just want to compensate it for aging or the other instabilities that we see, so we keep the pull range relatively low. So you'll typically see the pull range of a TCXO around 10 part per million.
Yeah. Anyone else questions? Because I still have some more questions.
Okay.
That's
Okay,
great.
so I get this question often, actually. Is there an oven-controlled TCXO? Like placing a TCXO in an oven, basically.
You could, but there really would almost be no reason to do that. The space that you take up with your TCXO package is going to take away from the crystal that we would want to use. The TCXO itself will vary a little bit, so you will see some more instability in the TCXO than you would in a crystal, depending upon how linear the temperature response of the TCXO is. If you happen to hit a non-linear area of the TCXO, it could actually be worse than using a crystal. We would tend to suggest using so the answer is no, you don't typically see an OC TCXO, although it is an option. And I would, if you can put your TCXO by a power transistor and basically create an OC TCXO yourself.
Yeah, exactly. Yeah. No, but I mean, I see your point. That perhaps is the precision of the whole process. That's you can't improve it. So you hit basically a limit. So another question that I often get also is there an OCXO that, I mean, I don't know what we have to change the word oven to, but if you use a Peltier element to avoid like a Peltier element that you can basically do the cooling as well. Is there such thing? Because we use this for lasers in rubidium, so I was wondering if the same thing exists.
So the answer is it doesn't exist commercially. We've seen those types of things in research type of environments, but at this point, the oven control has been good enough to support the temperature ranges that we need to see. One of the reasons why we might want to do something like that is if you're trying to get an OCXO to work over a 125 degree C temperature range and there's no semiconductors that would allow us to do that, then we might want to do something in terms of, cooling to help maintain the temperature of the crystal at a lower area. But in commercial applications, we don't see that.
Yeah.
It's also
another question is about aging, since you said the temperature really affects the aging. So is it fair to say, like usually with OCXO, aging is a bigger problem because you're operating a high temperature?
The answer to that is no, and that's because the crystal itself is maintained in its own hermetic environment, and so we don't see the changes that we would see that would drive the aging curve. It actually helps to a certain extent because the crystal will settle faster, if you know what I mean. It will come to a normalized state faster.
So that means also perhaps that preferably you have to keep the OCXO always on rather than switching on or off, because
yes,
so
OCXOs like to be turned on. They don't like to be turned on and off.
Yeah. So when you look at the literature of all these oscillators and everything, like somewhere I think beginning of 19th century, there was something was introduced. Again, this was more for the mechanical oscillators. two pendulum clock. I don't know if you're familiar with that. Like what basically was one piece that was actually, I don't know the details of it. I mean, one piece was oscillating and one was observing or something like this. And that gave us a huge performance, like the best you can get basically from pendulums. I was always wondering, is there a version like that also with crystals, or do we have something like that, like a double thing that uses anything of that sort? No?
Unfortunately not. The frequency of oscillation is much too fast.
I see. I see.
And actually
Okay.
the frequency is contained inside the quartz blank. We actually can't see that. So no, we don't have that type of pendulum type.
Mm-hmm. And then there is this Q factor that is used, is basically on one like, let's say induction of energy, how long it takes for the ringing, and that usually determines how fine you are, like let's say in or an oscillator. Do we still use that one or not? Like I always see ppb, ppm, like all of these things. Like, is it related to that, or?
It certainly is. You cannot get the higher the Q, the more stable the resonator is. But you can, by defining Q, you can affect other parameters to the crystal in terms of electrode size or the mounting that we use and that type of thing. So we prefer you to approach it as a black box and tell
Yes.
us what you need to get out of that black box, and then we'll take care of the sub parameters inside. But Q is certainly an important parameter for crystals. Like I said, you can't get, the Q of the crystal determines the stability that you're able to achieve. And one of the things we do in our OCXOs is we use very high Q crystals. We use crystals that are contained in a vacuum environment or a nitrogen, very dry, inert type of environment to give us the best oscillation and the best Q characteristics we can get.
Wonderful. Any more questions from the audience? Okay.
Yeah,
Seeing none.
maybe just one
Okay,
last
good.
question on
Yes, go.
the atomic oscillator Rubidium one, referring, like repeating the same question that Ahmad had on an on and off cycle. What is your retrace performance here?
So with this, it's much more relaxed. With 5 minutes of disciplining, I think the atomic standard will be up and ready to go and producing a disciplined output that you're able to use. The warm up and the atomic standard is so much faster than the crystal oscillator. So in that regard, the need for disciplining is a lot less than what we see. So the duty cycle, you can have it off most of the time and then turn it on when you need it.
Okay.
Wonderful.
I
Okay.
think really just
Again,
to
yes.
kind of round that out for any oscillator, for the more consistent you can have the duty cycle, the longer the runtime or the less time it's off, the more stable of a mechanism you'll have.
Yeah, that's like like how with the Q it is basically. If it's more selective, it can ring faster, so it's more stable. Okay. Any more questions?
Is it based on coherent population trapping, this oscillator?
Could you repeat the question, please?
Is this a coherent population trapping, like the classical CSAC?
Yes.
Okay. The interrogation technique, that's what I was asking.
Very similar.
Okay.
Okay. Seeing no more questions, thank you very much, Kory and Miguel. Like, so the recording will be on the website, and again, thank you for today's I'll call it lecture.
Great. Thank you, Ahmad. We appreciate
Thank you.
the opportunity.
You're welcome. Okay. Bye, everyone.
Bye, everyone.
Have a great day.
Bye.